actually extra harder than this one because we started with the EX and we are in the polynomial function. Is orthonormal basis is really ugly. I don't know if you remember your calculation. There's just so many coefficients, and pi mathematically even breaks down if you go to degree 7 or 8. So first you feel that pain by trying that same technique from the earlier problem, and have to try a slightly different way. So here's how it goes. E to the x, if you imitate the earlier one, we need power series, right? But I don't even know how the Fourier series of the e to the x goes, or between the bound -1 and +1. But what we have is convenient Maclaurin-Taylor series, and these are made out of this infinite basis, right? So our h is 1x and x squared, and I'm explaining this method on earlier one. It gets difficult, so we decided to focus on that phenomenon that if there is such u0, that v minus u0 is supposed to be the minimum, right? And try to contradict that. And that's the idea. So forget about actually doing the inner product and showing that it works out nicely. This orthonormal basis, P0, P1, by Gram-Schmidt process, it exists. But their shape's ugly, and we have no idea what is happening to the coefficient of this. And if you look at this calculation that I earlier here, to conclude, this tail part is not surprising. It's not going to surprise us. It has a lot to do with how the coefficient behaves right here. Very specific information is used, right? Not all the functions has these Fourier expansions. That's why. So if you don't know how this function behaves with this orthonormal basis you choose, what does the coefficient behave, it's very difficult to apply that technique. So here's a nice idea. Let's use the phenomenon. If there is a such u0, such a v minus u0 orthogonal to everything else in H, which is whole polynomial, then it's supposed to be the minimum value, right? Then we have this polynomial degree n, right? And this one, I'm skipping this calculation. The metric e to the x and tnx, this is the Taylor polynomial. The power series is cut out in degree n, right? That's actually a polynomial here, stopped at n. If you measure this distance, e to the x is the target, tnx is kind of rational approximation, polynomial approximation. The metric induced by the inner product is actually approaching 0. So as we increase this degree more and more, we're finding a higher degree polynomial. Not just that we know that's an approximation, not in just vague sense of approximation. It's an approximation with respect to the metric induced by the inner product we just defined. That's what calculation is. So with respect to that metric, this T1 is awfully close to EX as you increase n. But we claim that U0 has that orthogonality property, therefore this is the minimum, right? No matter what polynomial you choose, then if you look at, to apply the theorem, the H has to be finite dimension, right? So you can just go ahead and choose n that is greater than L. L is a degree of U0 that's supposed to be polynomial from H. Just choose anything greater than L. And you look at the PNR, there's a polynomial degree up to n. If you remain in here, that is your H, like Hn. Then theory applies. This Ex minus U0 is supposed to be the minimum as U varies within this finite dimension of this space, right? So this Ex minus U0 is supposed to be the minimum for Ex minus Tnx, which is a degree n polynomial. Correct? But this never changes as we increase, change the n to n plus 1, n plus 2. They're always a minimum, no matter what your finite dimension degree n polynomial is. This is always a minimum. But we just show that this one actually approaches 0, right? And this one never changes. There's one polynomial u0, Ex minus, the metric of Ex minus u0 is the smallest you're going to get. But if you look at, cut out this arbitrarily large finite dimensional space, there is this particular approximation that approaches 0 that violates this minimum, unless this is a 0, right? You have to show that e to the x is not a polynomial with respect to the limit is never 0. If that's clear, then this one will go eventually below that bound, which never changes as n changes. Therefore, it contradicts the fact that this is the minimum. Or ex, the metric, is 0, therefore ex is the polynomial. But that is not true. Because if you plug in, well, that's a little argument requires that to show that. How any part that you don't understand, the argument of this thing? That was pretty hard. Part B, to discover, to Taylor polynomial, how that interacts with the metric and the meaning of that orthogonal condition, to translate it to minimum value, which was a theory stated in the lecture part. L is the degree of U0. Very good. That is the key part. Degree of L0, degree of U0, that's a polynomial, so it must have a degree. It's not going to infinity. You fix it in there, then try to make this n really large so that L is included. The U0 is the part of this degree less than or n. So U0 is in here, right? Degree less than n. And there's always this Tn within that finite dimensional property that this metric is very, very small. But this one is just not changing at all. You can't win anymore if this guys go below arbitrarily close to 0. That was the logic.